Okay, welcome everyone to the fourth lecture of the Bootcamp. Just to go over some housekeeping things, uh, I'm not going to see you for a week. The next class is on Wednesday next week, and that's be Wednesday, and then the last class is on Friday next week. So in the interim week, the website is missing some things, and some links from previous lectures are dead. So I hope to have that very polished and beautiful before lecture next week. So at the end of the last class, we were talking about dealing with files and folders on your computer and how to navigate your file system in R and working directories and paths and things like that. And I thought that there were some things that I thought there were more things I wanted to get into, but after Unlink, there are things I could get into, but there's really nothing else that I feel like you guys should be aware of in the context of this class. Do any of you have any questions about what we talked about at the end of class? Okay. All right. In that case, the notes for that right now are not in good shape, but they will be in a week or before that, I'm hoping. So today I want to talk about, we're going to talk a little bit about reading and writing data, but I think I'm going to do that towards the end of class. But we're going to talk about another bulky topic that R is known for, which is doing statistics and statistical distributions and the statistical functions in R. And that gets folded in with doing simulations in R. And we're also going to do some very basic modeling. I could teach an entire semester-long course on any of these topics. So this is going to be a sampling, but I think it'll be a useful sampling. So I'll teach the audience that's here today. How many of you have taken AP Stats or a college level stats class? Okay, all right. So there are all kinds of statistical distributions, which are really just mathematical functions that you can use for different purposes for trying to model systems. That's all very meta. So I'll try to bring it down to some distributions that are more practical and easy to understand. So if you want to take a look at all of the distributions that are available in R, you can just type help and look for distributions. And the help page for distributions will give you a list. There's over a dozen of statistical functions that come packaged with R. There are even more statistical functions that are in packages that other people have written that you can get with the install.packages function. But these are the sort of known and sort of useful ones. So I'm going to talk about the normal distribution and the binomial distribution. The normal distribution is very important, although it's a little bit harder to understand than the binomial distribution, where the binomial distribution is also important, but it's very concrete and it's easy to talk about the mathematics for the binomial distribution. So let me go to some notes. I'm gonna the current statistical functions notes. Okay, the current statistical functions notes haven't. This is a document that I wrote a couple months ago for a class that I was in, and it definitely applies in this lecture. But I'm gonna basically all of the background I'm giving now, I'm going to put into the notes and then link to this page. But right now, it just links directly to this page. So the normal distribution is defined by this function for the normal distribution, which is if you're not used to dealing in statistics or doing a lot of math, there's like a lot going on here that is kind of hard to parse. So basically, all you really need to know is that this function takes. You specify two parameters for this function, mu and sigma, and then given any x, this function will produce a value. Most of the time when you see the normal distribution, sigma is equal to 1 and mu is equal to 0. And sigma and mu sigma represents the standard deviation of the normal distribution. Mu represents the mean of the normal distribution. So when you draw the normal distribution, I was going to draw on the board, but actually let's just draw it in R. So in order to use this, this mathematical function is a function in R. And that function is called dnorm. And if you look at the arguments for dnorm, you can see that the arguments for dnorm map identically to the parameters that you have to specify for the mathematical function of the normal distribution. So, x is just whatever value you're computing on, whatever you want to. The normal distribution is defined as a function of x. The mean is the same as mu in this equation, and SD is equal to is equal to sigma in this equation. So if I ask for dnorm of some number, let's just say 0, it will plug 0 into this mathematical function, and by default, as we can see, the default arguments for this function are that the mean mu is equal to 0 and sigma SD is equal to 1. So all I have to do is specify x, and I get a value back. So, yes?
What is the log is equal to false for?
Let's see. Honestly, it's not something I use, so, like, often. Okay, so there you go. If log is equal to true, then the value you get back is the log of the value you would get back if it was equal to false. Does everyone understand that? Some people, the log normal distribution is is just another distribution that is appropriate for some statistical operations. So if you just want to use that, it's an argument you can specify. So we don't just have to pass in single values as arguments to dnorm. We can pass in vectors as well. So I'm gonna create this vector here. Let me do it over here. I'm just gonna use sequence, and I'm gonna make a vector from -3 to 3, and I want to separate that by a pretty small margin, so we'll call it 0.01. And so that gets me back this huge vector of, applying this function, considering that the mean is equal to 0 and the standard deviation is equal to 1, to all of these values separated by 0.01 between -3 and 3. So we can plot this really easily using plot. And we get this bell curve that I imagine you guys have seen before when people talk about the bell curve. They're talking about the normal distribution, and this is what it looks like. We can make this look nicer by saying, that the type of this plot, we want to make a line plot, and instead of just having the index on the bottom, we can actually specify this sequence as the x values. So if you go through and you plug in, all of the individual values, that can get infinitely small if you want, between -3 and 3. This is, the result that you get from this, bless you, that you get back from this mathematical equation, is plotted on the y-axis. So this is what the probability density function, which is just this function, this is what it looks like when you draw it on the x and y-axis. Does everyone understand that and what I'm talking about? Okay. I just want to, I know that people have different math backgrounds, so I want things to be clear. So, okay, so that's pretty straightforward, I hope. So D norm, and the sort of D family of functions will give you, as long as you specify some parameters, they will just give you results depending on the mathematical functions that they're defined for, which you can see in all of these different statistical functions when you look at the distributions help page. So a more concrete example of this would be if you want to get results for the binomial distribution. You can use dbinom, which is probably up here. So the binomial distribution, let me get the formula from Wikipedia. The binomial distribution is just this equation, where you specify these three parameters, n, k, and p. Let me back up a little bit. The usefulness of the binomial distribution is when you're trying to find the probability of, out of a certain number of events, after a certain number, within a certain number of experiments, a proportion of what's the probability that a certain proportion of those experiments will be, I should have backed up even further. So I'm sorry, I'm doing a poor job at this. The binomial distribution is important when you're dealing with results that are binomial in that they can either be one of two things. They can be true or false. A coin flip can be heads or tails. The result can be 1 or 0. Someone can have a disease or they don't have a disease. And so you can model that using the binomial distribution. So if you want to know the exact probability that out of a certain number of experiments, a smaller number of those experiments are true or are one of those binomial choices, then you can use the binomial distribution. What you have to specify is the number of experiments that you're doing, the number of experiments that turn out positive or true, and also the probability that one of those experiments will be true. So, for example, if we wanted to ask the question, if we wanted to say flip 10 coins, what's the probability that 5 of them will be heads, given that we're flipping a fair coin? In R, we can answer that really easily using dbinom. So dbinom also has 3 arguments, but they're kind of different. X is the number of trues or the number of positives, the number of successful trials that we want to find the probability for. So in this case, we're going to say 5. We're flipping 10 coins, so we want to find the probability that 5 out of 10 coins will be true, given that the probability of being heads is 0.5, because we're specifying probability out of it has to be a number between 0 and 1. Does everyone understand that? I messed up a little bit in the beginning. Okay. Oh, go ahead.
First on the slice
Sure. So we want to know the probability that, um, given the fact that we're flipping 10 coins, we want to know the probability that 5 of them will be heads. So that's the question that we're asking. So if I run this function, I get back this number, and this is the probability that 5 of them will be heads. And a simpler, you can simplify this like as much as you want. You could say, what's the probability of one head given one coin flip? What do you guys think it'll be? Yeah, it'll be 0.5. So if you were to plug all these numbers into this mathematical function, you'd get the same results. Does everyone understand this notation of one number of like the choose notation? Okay. So if we go back to this help page, D whatever distribution you're dealing with, just to reiterate, will you provide parameters to a certain function, and it gives you back the results of considering the parameters that you provided. So now I want to talk about. So there are these with the statistical functions in R. These families of statistical functions are divided up by like the D, P, Q, and R families, and I'll get into what each of those do. And then, of course, they're also divided by the family of what function they are, whether it's norm, binom, the beta function, the gamma function, the hypergeometric distribution, what have you. So my point is that these D, P, Q, and R ideas that I'm going to present are the same across the different distributions, and then you can mix and match the kind of distribution and the kind of functionality that you want out of D, P, Q, or R in order to get whatever result that you're looking for. So before we had, I'm going to go back to the normal distribution. So this is the normal distribution with mean 0 and standard deviation 1. And in a lot of statistical testing, what you do is, I'm going to talk about like the importance of the normal distribution first. There's this idea of, I'm going to come back to this. Because we'll get into it. Right now, I'm just going to like tell you what these, what the P, Q, and R functions do. So the P function, or in the case of the normal distribution, P norm, will tell you the integral under this function, under this curve, from negative infinity to whatever number you specify along this x-axis. So, for example, if I say, if I give this -1, all of the integral from -1 all the way out in this direction to negative infinity is around 0.15. If I say 0, it's 0.5 because this the normal distribution is the same on both sides, and so you divide it perfectly where the mean is. The mean is at 0, and so half of all of the area under this curve is to the left of 0. Yes?
Why are we taking the integral of the curve? I mean, so the P norm of a certain x is not just the probability of that x, it's the probability of everything before that as well.
Yeah, so it is I wouldn't think about it in terms of, I wouldn't think about how this function works in terms of probabilities yet.
Okay.
As much as you should just think about that p norm gives you this integral, and then thinking about
But then is that the probability of that x value, or of all the values up to that x value?
so if you're getting into probability, if you were, say, like taking random draws from the normal distribution, which we're going to do, the probability that you draw something that's less than 0 is 1/2. So you can think about it. So in that way, you can think about it as a probability. But as far as what these p family of functions actually do, and like how you should think about what they do, you should think about it in terms of integrals. I don't know. At least that helps me. But if it helps you to think about if it helps you to think about it that way, like, it's not wrong. I'm just kind of giving like the strictest version of the definition of what these functions do. With p norm, you can also specify the mean and the standard deviation, and if we had a different curve drawn, then in order to get accurate information from p norm, we would have to specify that mean and standard deviation. This lower tail argument is the same as saying 1 minus p norm or whatever. So if I want the integral of this function, before -1, if I say -1 and then I set this equal to true, this is the same as what is that? Hold on a second. You know why I'm backwards, because I'm doing it with a negative. So if I do p norm 1, so this is everything from the left of 1 up to 1, and then I say the lower tail. Hold on a second. Oh, okay. Sorry, I'm a little mixed up. The lower tail is normally equal to true. So if I say the lower tail is equal to false, this is the same as when the lower tail is equal to true and you say 1 minus this p norm. So in essence, what I'm saying is that if you want to get the integral from, say, -1 to infinity, you can either say p norm of -1 lower tail equal to false, or you can say lower tail equal to true, which is the default, and just say 1 minus that p norm. Do you guys understand why that is? Just to be, to be explicit, the integral of this entire function between -infinity and infinity is 1. So if you take the integral from -infinity to 1, and you subtract that from 1, you'll get the integral from -1 to positive infinity. Okay, everyone good? Okay.
I didn't really understand the lower tail. Is it false and lower tail is equal to true? What do those two specify?
I'm sorry, what was the last part of your question?
What do you mean by lower tail is equal to false, or lower tail is equal to true?
Okay, so you are specifying which part, you're specifying which integral you're doing. So if you're doing the integral of the lower tail, you're going from -infinity to the x that you're specifying.
Yes.
And if you say lower tail equals false, then you're doing the upper tail, which means that you're starting at whatever you're specifying and going to positive infinity. Although upper tail is not a parameter. Yeah. It's not, upper tail is not an argument, but that is that's the way that they wrote the function. So to have like a more concrete example of this, before we were talking about the binomial distribution, and if we wanted to know the probability of flipping 10 coins and exactly 5 of them being heads, we can use dbinom. But what if we wanted to know the probability of at maximum 5 of the coins being heads after flipping 10 coins? So in this instance, we could use p binom. And with p binom, you have to give it the same arguments. So you still say, you're going from 0 to, you're finding the probability of, or the sum of the probabilities of 0 heads, 1 heads, 2 heads, 3 heads, 4 heads, 5 heads, out of 10 coin flips. And this is a fair coin, so we're going to say the probability equals 0.5. And as you can see, that will give you a larger number because you're including more probabilities. And we can show this like very explicitly by using dbinom. So remember, dbinom will just give you the exact probability of getting exactly 5 heads out of 10 coin tosses. But instead of giving dbinom one parameter, we can give it the vector of the integers between 0 and 5. Then we can specify the other parameters. That'll give us back a vector of probabilities. And if we sum this vector, it should give us the same number as p binom, and it does. Do you guys have questions about that?
Why do you have to sum it to find, like, if you're taking the interval from 0 to 5, wouldn't that be the equivalent?
Oh, sure, it is. I'm just taking the sum. I'm just showing that the sum of the d binoms is the same as just saying p binom.
Oh.
Does everyone else understand that? Okay. Okay, so the next function, this family of functions, is the Q family. The Q family of functions is the inverse of the P family of functions. So if we say Q norm, and we're going to leave these default values of me equals to 0 and standard deviation is equal to 1. If we say Q norm and we give it one of these values on the y-axis, so if we give it one of these like results of this normal distribution function, it will give us the x value. So I guess like the best way I can estimate this is to kind of eyeball it on this graph and say if we give this function 0.2, it should give us something around -1. And it kind of does. And in fact, to show you where this lines up, we can even plot this on this curve. So I'm going to use the points function. I actually don't think we talked about the points function when I talked about plotting, but points it's the same as the lines function, but just for plotting more points onto a graph that you've already plotted. So this is a function that would normally come after some plotting function. This will add another layer. So we want to plot on the x-axis is this Q norm, on the y-axis is 0.2, and I messed this up. I probably use backwards, but I shouldn't. Right, this is y. Oh, it's because I did 0.2. I like didn't know. I meant to do Q norm. Oh no. Sorry. Oh wait, no. Yeah, it's because I have this backwards. This is the y, obviously. Now it's upset. Or it's just plotting it off of the plot. Oh, because, the x we want is -1. Sorry, I'm all turned around. Okay, so with Q norm, we give it 0.02. Really? Hold on. Oh, this is 0.02. Sorry, I did this before and I was doing fine. The x value we want is 0.1. I'm sorry, I'm no, the x value we want is Q norm because this is negative. Oh, I know what I'm doing. Oh no, it comes out negative. So this x value is right. We want it to plot on 0.02. It shows up in the wrong place. Right? I mean, let me check with you guys. You understand what I'm trying to do? Q norm is the inverse of P norm. So if I give it a, so I want to plot this point right here. I give it 0.02. And that gives me, so to illustrate this more, sorry, let me illustrate this in a non-graphical way first. So once we say Q norm of 0.02, we give it one of these, values on the y-axis to get a value on the x-axis. If I then turn around and take this value and I plot, and I want the P norm of this, so this is the integral from -infinity to this value, then I get back 0.02. So in that way, you can at least see that they're the inverse of each other. I'm freezing up on why this isn't working, but once I have a minute, I know that I'll think of it. But does everyone at least have an understanding of Q norm? Sorry about that. So now of all of these, the most fun, in my opinion, is the R family of functions. So with R norm, you specify the mean of the normal distribution that you want to work with, the standard deviation of the normal distribution that you want to work with, and then the number of random numbers that you want to draw from that distribution. So if you want to simulate random draws from a normal distribution, this is a wonderful way to do it. So I can just ask for 10 random numbers from this normal distribution, and I get back a vector of 10 numbers. In sort of a more relatable way, if I use R binom and I specify the number of numbers that I want back in a vector, so I'll say 10, the total number of coin flips I want to do in one experiment, I'll say 5. And then the probability of a coin landing on heads, we'll use a fair coin and say 0.05. I get back a vector of where each element in this vector is the number of heads in 5 separate experiments of, in 10 separate experiments of flipping 5 coins. So I did one experiment, flipped 5 coins, got 3 heads. Another completely separate experiment, flipped 5 coins, got 3 heads again, and so on and so forth. And that's what this vector represents. So this is a wonderful way to simulate taking random draws from any of the distributions that are included in R. So if I won't get into the details of the kinds of distribution of explaining these different distributions, but if you wanted to have random draws, if you wanted to like have random data of the amount of time between like seeing a shooting star, you could use the Poisson distribution. If you wanted, if a lot of data is kind of bell shaped, and so you can use the normal distribution. And if you're dealing with data that is more natural to think about it logarithmically, you can use the log normal distribution, and kind of like so on and so forth. You can generate random data in this way. Yes.
You said if you don't specify like the 10, 5, and everything, where does it take the 10 random draws from? Like when we just put R norm 10, like where did this come from?
Oh, sure. So these, for R norm, the default values are that, the default arguments are that mean is equal to 0 and standard deviation is equal to 1. So if I explicitly specify the mean to like be equal to 50, and if I make the standard deviation very small, like 0.01, these will be 10 random numbers from a normal distribution that looks like this, but they'll all be close to 50, as you can see. So this is a great way of simulating data from all these kinds of distributions, and it segues us perfectly into simulations in R in general. Simulations in R, there are 4 useful kinds of functions for immediately doing easy simulations in R. One of those kinds of functions are the different R norm, R binom, the R family of statistical functions. So we've covered that. Does anyone have questions about the R functions before we really get into simulation? Okay. So one way is these R functions that are all coupled with these distributions. But probably the most like intuitive function is this, in my opinion at least, is this function called sample. So sample has some arguments which you can specify, but we'll start off with like the simplest kinds of arguments you can give to sample, then we'll get more complicated. If you wanted to sample from sample, it does what you think it does. You provide it with a vector, and it will, if you just provide it with a vector like this, so this is the vector of the integers between 1 and 8, if you just provide it with a vector like this, it will sample from this vector without replacement, and it will return a numeric vector with the numbers that it drew from this vector in the order that it drew them. So if I run this code, first from this vector of 1 through 8, it drew 3, and then it didn't replace it. So now the vector got smaller and only has 7 elements. Then it drew 6, it didn't replace it, and kept going until the last element in the vector was 5, and it was forced to draw 5 because by the time it drew it, there was only 1 element left in that vector. Does everyone understand that? You could also specify, replacement. So if you, the default is to draw without replacement, but if you want to draw with replacement, you can just set replace equal to true. And we got lucky, it drew 8 twice, so you can see that every time it randomly drew from this vector of the integers of 1 through 8, you can see it drew 8 times, which is the default since the length of the vector is 8. And you can see you can see that it replaced the elements because we drew 8 twice, and we drew 1 twice. If you want to sample from this vector of 8 things, but you don't want 8 results, you want only a certain number of the results, you can specify size, and we're going to say size is equal to 3. And so this will give you back a vector of 3 randomly chosen elements of 1 through 8, and chosen with replacement. You can also say that replacement is equal to false, and now it's the same experiment, except every time, after choosing the first number, 1 is eliminated from being a member of the vector of things that you're choosing from. Does everyone understand that? So, if you want to simulate the values of rolling a single die, that's really easy to do. You can just pick from the numbers between 1 and 6 randomly. If you're just picking 1, then replacement doesn't really matter. But if you pick multiple, so this is like 1. This is an example of having 1 die roll. So we got 1. If you want to roll 10 dice, then this is a vector of the values you get back from 10 dice rolls. Does that make sense? So if you want to, you don't have to sample from numeric vectors. You can sample from vectors that have strings. And now you've just sampled from this vector in 10 different times with replacement. If the vector is shorter than the number of results that you want and you set replacement equal to false, it'll be upset with you because it can't give you back as many results as you want. All right, I guess there are no other arguments I want to talk about to sample. So sample is a great way for generating your own random sort of data. Talking about these functions that draw randomly or pick randomly, either draw randomly from a distribution or pick randomly from a vector, you might, as I did a few nights ago, you might want to be able to know what you're randomly going to draw in order to talk about it, for example, in an R Markdown document. So, like, if you're giving some presentation and you're kind of giving like an example of a random draw, and you want to say, hold on, let me go back to our dice rolling example. So we'll have a vector of 1 through 6, roll 10 die with replacement. So if you want to say something like, that there's this like streak of 3s in the middle, and you want that, every time you run this function, of course it's going to be different. So in order to fix this, you need to do something called setting the seed. So these random numbers are actually not random in sort of the way that we naturally think about randomness and unpredictable events. If you were to analyze millions of these random draws from any computer, you could attempt and sometimes successfully reverse engineer the way that these numbers are picked, and you could make predictions about what the next number what the next number that's going to be picked is, because computers are incapable of like simulating true randomness, and the way that they pick random numbers is that they start off with some seed in an algorithm that then dictates the next number that it's going to pick, and every time you run sample, or every time you do one of these random draws, that number gets updated. So in order to fix this number so that you can talk intelligently about, or not you can talk intelligently, but you can talk like deterministically about what you're drawing, you have to use this function called setSeed. So with setSeed, you just specify an integer. I like to use the date, quote unquote, which is just the result. Like today, I would say 1 minus 13 minus 2016. Of course, this expression evaluates to some integer, and then this integer, negative 2028, is set to the seed. And you can see when I execute this function, then I execute sample, so I do 10 dice rolls. This is the result. If I execute this function again, so I've reset the seed to this seed, and then I sample it again, I get the exact same numbers. So this is important in terms of people being able to reproduce your analysis. If for some reason your analysis is dependent on randomly sampled numbers or anything random in R, it's important to set the seeds so that your later analysis, so basically so that these values are deterministic and they don't have an effect that you might not want on your later analysis. For example, if you don't set the seed, the first time you run through code that's like drawing from a normal distribution, it can all draw things from around the mean, which is what should happen. But in like multiple iterations of drawing random numbers from a normal distribution, you'll get some numbers that are towards the ends that are rare to get, and that might throw off some later analysis or some later conclusion that you might make. Does anyone have any questions about sample or the basics of like these seeds and stuff like that? Okay, so sample is great, and you can adapt sample in many different ways. Something that I use a lot with the R family functions and with sample is a function called replicate. So replicate, you give it two arguments. The first argument is the number of times you want to replicate something. And the second argument that you give it is an R expression that will be replicated the number of times that you specify. So let's say that I wanted to roll 10 die, or 10 dice. I don't know why I keep saying that. I want to roll 10 dice, and then I want to find the mean of those 10 dice rolls, which in this case is 3.3, but if I run this again, it'll be something different. And then I want to replicate this R expression 10 times. So I want to get 10 means of 10 dice rolls each. So if I just take this expression and use it as the second argument to replicate, and I run this, I'll get back a numeric vector of 10 means. And replicate is pretty flexible, and basically for any like one-liner lines of code for either doing some simulation or really anything, it'll work for you, and it will return things in this vectorized format. Let me see something here. But let's just say that so let's just say that I wanted to run 10 simulations of rolling 10 dice. If I get rid of saying that mean parameter, that mean function, if I use replicate, instead of giving me back a vector of 10 means, it'll give me back a matrix of 10 simulations of rolling 10 dice, which, depending on the kind of simulation that you're doing, might be something that you want. So replicate, in other words, if the expression that you give to replicate produces a vector like sample does, then the result of replicate will give you back a matrix, because each here. In fact, we can illustrate this better if we do like fewer replications. So now we're doing 5 replications of 10 dice rolls. So as you can see, each group of 10 dice rolls is its own column. So if the value of the expression that you're giving to replicate produces a single value, you'll get a vector back from replicate. If the expression produces a vector, then you'll get a matrix back from replicate, where each column, is one of those expressions and then one vector that you would get back. Does anyone have any questions about that? Okay. So yeah, so that that's replicate. It's fairly straightforward, I think. Then replicate is actually part of another family of functions that I want to talk about that are good to use they're great to use for simulation, but they're also good to use for, they're also just like good to use generally. And this is the apply family of functions. So the way the apply family of functions work is that you specify a data structure, usually a vector or a list or a matrix, and then you specify a function, and in some way that function is applied to the data structure. And I'll show you what I mean with some simple examples first. So the apply function, there's a function called apply. This is kind of the grandfather of the other apply functions. And the apply function works on matrices. So let's say we have this matrix of 10. Let's say that, for some reason, let me make sure. Let's say for some reason we were given this matrix of 5 simulations of rolling 10 dice. So we'll put that in a variable called dice. And we want to find the mean of each of these simulations of rolling 10 dice. And we want, we want those means as a vector of 5 means. So what we can do is we can specify our apply takes 3 main arguments, and we can specify the data that we're going to apply a function to, which is dice. You then have to specify the margin that this function is going to be applied to. So that is either the rows or the columns. The rows is represented by the number 1. The columns are represented by the number 2. We want to find the mean of the columns because each column represents one simulation of rolling 10 dice. So I'm going to specify 2. And then the function that we want to apply to each of these columns is the mean function. And so we pass the mean function as an argument to apply just by its function name. So we don't say like mean with parentheses or anything like that. We just say mean. And so if we run this line of code, apply will go through each of the columns. It will find the mean of each of the columns, and it will give us back a vector of each, a vector of the means of the columns. So, the first element of this vector is the mean of this column, of the first column here. Bless you. So with apply, you can you can get you can do some more advanced things, and I'm going to get into some of the apply functions. Like the simplest one to use, I believe at least, is sapply. So there are even other apply functions outside of this. I got to this help page by doing $sapply, or you can do $lapply. The differences between these functions is really just the data structure that they're applying themselves to. So these apply functions take other functions, they take data, and they apply those functions to the data. So like lapply you use with lists. Sapply and vapply, you can use them both with vectors, but I have a better experience using sapply. So let's say that we make some dice rolls. Call this one rolls. And we'll just do a simple sampling of 10 rolls. And we'll store that in a variable. And then, let me put this. So let's say we want to go through this vector and apply some function to this vector and to all the elements of this vector that isn't defined in R. So we want to write our own function. So let's say that instead of let's say that I want to, for every element in the vector that we're going to go through of dice rolls, if a roll is less than 3, then I want to produce some string that says less than 3. And if it's greater than 3, or greater than or equal to 3, I'm gonna produce some string that's greater than or equal to 3. So this isn't, this is kind of an arbitrary example, but there is no built-in operator or built-in function in R that we could use to do this right now. So I'm going to define a function the way that we've been defining functions, and I'll just call this function string3. So this function takes one argument, which I'm going to call x. The functions that you pass into the apply functions have to at least take one argument, because that argument is what's going to happen is that each element of the data or of the vector that we're going to go through using sapply, that element is going to take the place of, or x is going to take the value of that element when this function is applied to each element of that vector. That was very circular. I guess let me show you an example, and hopefully that will make more sense. So string3, you get some number x, and I'm going to say I'm just going to write a simple if statement that says if x is less than 3, return less than 3. Otherwise, return greater than. Okay. All right, so let me define this function. Great. Just make sure it works. Spectacular. So now I have this vector of rolls, and I want to apply this function to each element of this rolls vector. So I'm going to say sapply. The first argument that I'll give it is this vector of rolls. Oops. And then I will give it this function that I created called string3. And if we execute this, it will give me back a vector of strings where this string3 function is mapped to each element of this vector. So for each element of the vector, this function is applied, and then the result of this function is returned in vectorized form, where the first element of the result is the result of this function for the first element of my roles vector. Does that make sense? This is like, this is kind of building up our abstraction of like using, or layers of abstractions of like using functions within other functions and so forth. So, does anyone have any questions? I'll let you stew on it a little bit. But you can use these apply functions. You can use these apply functions in many different ways, but you can definitely use them to make simulations. So, if I want to combine a ton of these things and say like, if I want to have, let's see what's a good example. Let's say I want to use, I want to go back to our friend and use our binom for randomly generating coin flips. So, just to review a little bit, with our binom, I can say that I want to run 10 experiments where we're going to flip 100 coins, and the probability of, we'll keep it a fair coin. We'll say the probability of heads is equal to 0.5. So this expression alone will give me, each time it will do 100 coin flips. It does 100 coin flips 10 times. And for each one of those experiments of 100 coin flips, first I got 53 heads, then I got 45 heads, and so on. So if we combine this with replicate, I can say that I want to do this. I want to do this experiment and find the mean number of heads that I get from flipping 100 coins 10 times, and I want to find 100 of those means. So I can do that using replicate, and it'll give me 100 means of flipping 100 coins 10 times. Each of these is a mean number of heads. And then I can use, I could use sapply, or I could even use replicate again. As you can see, sapply and replicate are on the same help page because what they do is very similar. So let me, I could do, if I wanted to, for whatever reason, I could replicate, I could replicate this 100 times, and that'll give me a matrix. That'll give me a gigantic matrix where, here we go, where where each of these columns is a replicate of, where each of these columns represents 100 means from flipping 100 coins 10 times. But as you can see, by combining these functions, you can very quickly build up a lot of simulated data. Because already, we have in one line of code, we have a 100 by 100 matrix of values that have already been aggregated from flipping 100 coins 10 times each. And I wanted to go back and so does everyone understand? Does everyone understand that and like kind of see the power in that? Yeah.
Could you just go through the function? So at first you've taken the mean.
Sure. You mean this?
Yeah.
Sure. Sure. No, that's a good idea. So the heart of this is this function our binom. So what I'm doing every time I run this function, I'm flipping 100 coins. I'm doing this 10 times, and each time I get back, and each element represents a separate experiment. So like in the first experiment, I flip 100 coins, I get 48 heads. In the second experiment, I flip 100 coins again, I get 53 heads. And the only reason I'm getting 10 is because I'm specifying that as the first argument of our binom. If I wanted, if I just want to do this twice, I could say 2, and it's the same experiment. So if I take the mean of this, I'm finding one mean of 10 separate experiments of flipping 100 coins. So out of 10 experiments, the mean number of heads for this simulation is 48.1 heads. And if I run it again, I'll get something different. So then I can produce multiples of these means by using replicate. So all I have to do there is use the replicate function. And let's say I want to find 10 of these means. I specify that for replicate, and it'll give me back a vector of 10 means. So basically, this expression, which produces a vector, if I use this expression in replicate again, or in sapply, or any of these, so sapply and lapply work on lists and vectors in the same way. When you use lapply, you'll get a list back. When you use sapply, you'll get a vector back if you pass in a vector. Where just apply is designed to work on matrices, where you're either applying a function across rows or across columns. And if you use apply on a vector, and the result of the function that you're using with apply is another vector, you'll get back a matrix, because every column, every column of that matrix is a result of that function being called once on each element of the vector that you're processing. Does that answer your question? Okay. Okay, so let's see here. There is a point I want to make. There are, because I don't know all of your math backgrounds, and I want everyone to understand everything I'm doing in this class. I don't want to get too much into the statistics and like the details of the mathematics. But there is something that I want to show, which I think is, I work in a department of biostatistics, so I think a lot of things in statistics are cool, but I think this is a powerful idea, and when you're programming in R, it comes up from time to time, and I think a good thing to keep in mind, which is this notion of the central limit theorem. So the central limit, sort of the weak definition of the central limit theorem is that if you have any distribution of numbers, and you sample from that distribution, the sample means will follow a normal distribution. And so I want to show that to you using R. And if you don't understand what I'm really saying, I hope to illustrate it with R. So let's start off with actually, let's even start simple. Let's start off with rolling dice. That's what we've been doing. So this code, this call to the sample function will get us one dice roll every time we execute it. If we if we specify 100 dice rolls, we can get back a vector of 100. And to quickly, another important thing is to quickly, when you're doing simulations like this, it's useful to visualize it. So, let's take a look at using hist. Let's take a look at how these. Here, I'm going to overwrite a variable we used before, rolls. So this is 100 rolls. I'm going to use hist to look at these rolls. What do you guys think this histogram will look like? You can, I just want to guess. You will not be penalized for being wrong. So we're rolling. Okay.
I feel like because it's okay, so we have 6 values that it could give out. And
Sure.
It has to give the size of 100.
Sure.
Essentially 100 values, which could be between 1 to 6.
Yeah.
So the histogram should have 100 values.
Should be what?
Should have. I don't know. It should either have 1 to 6, and then the number of times that they appear.
Sure. So it'll have 1 to 6 on the x-axis, or it'll be approximately 1 to 6. It might be like between 0 and 7 or something. But I guess what I'm really asking is, what will the histogram itself look like? Will it, describe?
Wouldn't that be just random?
So it will be. So the way that the histogram works is that for the numbers 1 through 6, each bar on the histogram hypothetically should be assigned its own number. One bar represents the number of 1s, 1 bar represents the number of 2s, and so on.
I would assume that the sum of all those bars would be 100. So they will have to be. Because they can, in all there would be 100 values.
Sure. So the sum of the bars will definitely be 100.
Yeah.
The sum of the y axes. But what I'm really asking is what will the
It should be approximately the same.
yeah. So the top. What I'm really talking about is the top of this histogram. So it should be approximately the same because there's no, there's no. The probability of any of the numbers being rolled is equal. This isn't a weighted die. So if we visualize the histogram, because we're only dealing with 6 numbers, it's it isn't shown very well, but it's approximately equal. And if we increase the size, and instead of doing 100 dice rolls, we do 1,000 dice rolls, it gets flatter. And if we do 10,000 dice rolls, it gets even flatter. And the more rolls we do, the flatter the top of this histogram gets. So this is a distribution. This is rolling one die represents a probability distribution where the only possible values are 1 through 6, and the probability of each value is equal. So I want to use this distribution to also, just as a fun fact, these kinds of distributions where the probability of all the value, where the probability of all the values, all the possible values are equal, are called uniform distributions. And so rolling a die is a classic uniform distribution, and if we take if we take the mean of rolls, so I'm paring rolls back down to 1,000 rolls. So actually, I'm going to pare it down. I'm going to try to show you the same thing with means. So if we do 10 rolls, we get a mean of 2.4, 2.5, 3.7. So as you can see, the mean is like bouncing around a little bit. Where if we do 100 rolls, we get 3.35, 3.67. You can see that the mean is like a little bit more constrained. If we do 1,000 rolls, the mean gets even more constrained. And in fact, I should have thought about it. I'm glad I'm thinking about this. Let's plot this, right? So, we want to explore the relationship between the number of dice that we're rolling in an experiment and the mean of the mean of all those rolls. So we can do this using sapply. So first we want to the best way to do this. Well, we can do this using sapply. So the size of the number of rolls that we want to do. Let's start out going from 1 to 1,000. So that's our data, just a vector of the integers between 1 and 1,000. And then the function that we want to compute is the mean of this sample. So we have to write a function. So we have to write it's a very simple function, right? This is just call this dice mean. It takes one argument, and all it does is it returns the mean of this expression of dice rolls, except we're changing the size. Okay, so does everyone understand how this function works? So like, if I just call dice mean and I give it 10, what's going to happen is it's going to roll 10 dice and it's going to return the mean. That's lucky. Okay. Oh, that was just luck that I got 2 integers in a row. So if I give it 100, then it's going to roll 100 dice and return the mean. So now what I'm going to do is I'm going to apply that function across the very simple vector of 1 to 1,000. So first it's going to compute the mean of a simulation of rolling 1 die, then a simulation of rolling 2 dice, etc. So this will return. Oh, this is a good question. So what will this return? So we're passing into sapply a vector of all the integers from 1 to 1,000. This function that returns a single value. So what should it return as far as like what should the data structure be that it returns? Is it going to be a single value? Is it going to be a vector? Is it going to be a matrix? If you have like no idea, well, never mind. I said this before. It's so stupid. So we're taking a vector, the vector of the integers from 1 to 1,000. So like imagine you have that vector and you're taking a function and you're applying that function to each element of the vector. So if we were to say there's like a mapping from like, yeah, so that's one way to think about it, is like, what does this function map each element of this vector to? So we've got all these individual values in this vector. You take one of those values and you apply it to this function. And that function maps one value to what? So
Size. So basically, how many times the dice would be rolled. Like basically that value. So in the end, we should be getting 1,000 values of the mean.
yes. So what's happening? Maybe it'd be better if I drew this. So like we have a vector of 1,000 elements, and it's all integers to 1,000. So what S applied does is it takes a function, which we're going to represent as an arrow. So you give it data, which in this case is this vector, then you give it a function, which in this case is this arrow, and it maps this value to some other value, and that value might be a vector, or it might be a single value. So the function that we have in this case, dice mean, takes one value, like I was using up here, it takes 100 and maps it to one other single value, right? Like it's not, I could write a function that takes the number 100 and returns the integers from 1 to 100. You know what I mean? That would be mapping a single value to a vector. But this function takes a single value 100 and maps it to, it returns a single value. You guys see that? Okay. If you don't, please raise your hand. So in this case, we're going through this vector, and like each element of this vector is siloed in one operation that we're doing with this function. So we're taking this value of 1, we're applying this function dice mean, and so what value should we, or what, well now I kind of gave it away, but like what should we get back? Like what is, not what is the number going to be, but what is it going to look like from doing this one operation? Is it going to be, are we going to get back a vector or a value? From doing this one operation. Yeah. So we're gonna get back a value, of course, and like it's whatever that mean is. And so we're gonna go through this vector and we're going to do this again. So we're gonna take 2, we're gonna apply this function, and what are we gonna get back? So we get back another value. And so we, in this case where what you're getting back from each operation, from each application of the function, is a single value. When you have a lot of single values in some linear structure in R, it is a vector. Do you guys see what I'm saying here? And in the same way, if we returned, if I wrote a function that takes one argument and returns all the values in a vector from, maybe I should just write it so you can see. So like if I wrote some function like from 1 to x. So this function is taking a single value, but it's going to return a vector from 1 to x, whatever x is. So if I enter this function into the console and then I do from 1 to x 100, I get all the integers between 1 and 100. If I say from 1 to x -10, I get numbers from 1 to -10 counting down. So in this case, we have a single value, and this function maps it to a vector. So if I were to say, if I were to use sapply, if I were to use sapply from like the, oh, actually this would be interesting. If I were to use sapply from 1 to 100 and provide it, this from 1 to x function that I just wrote, what kind of data structure do you think I would get back? Would it be a single value, a vector, or a matrix?
A vector from 1 to 10.
If I apply it like this.
Yeah. Basically 1, 2, 3, 4, 5, 6, 7, 8, 10. Wouldn't you just get that? Because you're changing values from, we're first making it 1 and you're making 2, and when you plug that back in, oh no, it would give you a matrix because each time, like if when you put in the value of x is equal to 9, then it will give you from 1 to 9. So it will give you 1, 1, 2, 1, 2, 3, 1, 2, 3, 4.
Do you guys understand what she's saying? You're right. Yes.
In that case, what would happen though if you had like 1 through 5 and then you had like 1 through 6? What happens to like the 6th element in the first row?
Yes, so while thinking about this, this isn't the best example because it won't always give back a fixed length. I think this will give back a list. Let's find out. Yeah, so in this case, we talked a little bit about, someone asked about ragged arrays, and I didn't expect you guys like to know that this would happen. I just kind of wanted to like reinforce that, like this point of like mapping from like one dimension to another. But in this case, because it's someone before asked about like ragged arrays, and so instead of giving back a matrix where like half the values are NA values, which you can imagine you could have like, the first thing is like from 1 to 1, so you could have 1 and then 10 NAs, and then you could have 1, 2, and 8 NAs, or 9 NAs for 1 and 8 NAs for 1, 2. Instead of doing that, it saves the space and gives you back a list of lists. So, this is a list of vectors. So the first vector in the list is just the vector 1. The second vector in the list is the vector 1, 2, etc. So it's kind of, it's like a matrix, but because this mapping doesn't provide a uniform length, it returns a list. So sorry, that's like a confusing note that I didn't really want to talk about, and I should have come up with like a better function that would have given back something that has a uniform length. But do you guys understand that? I mean, it is a good point to make, but not the point I wanted to make. But do you understand both things? Okay. Okay, so now, kind of like coming back down to what we were doing. Although I'm glad we did that. I think that that's important in thinking about how sapply works. So now we're back. So now we've got this function dice mean, which takes a single value, which is the number of dice rolls we're going to do, and returns a single value, which is the mean of doing all of those dice rolls. And we're going to apply that function to the integers from 1 to 1,000. So just to be wildly pedantic, what is the result of this function going to look like as far as a data structure? When I run sapply, will this be a value, a vector, a matrix, a list? Like we saw, it's not a list. Yeah. So it's going to be a vector because we're going through each element from 1 to 1,000. We apply this function dice mean. Dice for each element, we get back one value because we know that dice mean returns one value, and a linear the linear structure of multiple values is a vector. It's a numeric vector. Yes.
Would you expect the values at the end to be closer to each other than the values in the beginning because the sample size is increasing?
Sure. So you would, and that's exactly what I want to show you guys. So if we run this line of code, this doesn't illustrate that much, but if we plot this, so we're going to plot this, and on the x-axis we're going to plot the number of rolls, and on the y-axis we're going to plot the mean, and that's nice, but really we should make this to a line graph. As you can see, as the number of rolls increases, the mean becomes more and more restricted to what it can be. And we can even, if we go to 10,000 rolls, we can see that it becomes, it's consistently like infinitesimally smaller. Isn't that cool? I don't know. I personally think it's interesting. This is a weak version of the law of large numbers, which is exactly this concept that you talked about, which is that the higher the number of the more experiments you do, the mean of those experiments will converge to a fixed point as you do more experiments. And the law of large numbers and the central limit theorem go hand in hand. So now I'm glad that we got to talk about this and the law of large numbers and use it as a relevant example for s-apply. But I was on the way to telling you about the central limit theorem, which we can show that these sample means, which we get from to get sample means we need to do some different things. So now I want to get a collection of sample means, but from dice rolls where we're rolling the same number of dice each time. So I can do that easily, with almost the same code where the number of, I want to fix the number of dice that we're rolling, so I'm going to fix it at 100, and we'll play around with that a little bit. But for now, I want to fix it at 100, and I want 1,000 of these means. What function would you guys use to get 1,000 of these means? So yeah, so you really could use either. You could use s-apply, or you could use replicate. I kind of like the syntax for replicate better because you just take the line of code you want to do, you say how many times you want to do it, and you go to town. But you could also use s-apply. Using s-apply, you would get the same result, but with s-apply you would have to say that you're going through a vector of 1 to 1,000, and then you'd have to write a function to wrap this expression, and then you wouldn't use the numbers between 1 and 1,000. You see what I mean? In our example calculating these means, we used the x argument to specify the size, but we don't need, we don't need all the numbers in that sequence. So yeah, so you could use supply, but I would recommend replicate. So if we do this, we get 1,000 sample means. And if we look at, before I was asking you about like what the histogram of those dice of the dice roll results should look like. If we look at the histogram of these, so these are roll means. My naming hasn't been great today, but whatever, roll means. So if we look at the histogram of these roll means, they look sort of bell curved. And if we specify the breaks argument in histogram, there's only like a dozen breaks here, so we say like 100 breaks, which should be fine since we have 1,000 roll means what we're looking at. It even looks more like the normal distribution. And if we increase the number of replications that we want to do, so now we're calculating 10,000 means of rolling 100 dice, it looks even more bell-shaped. And at the more replications we do, this might actually take some time. The more bell-shaped it looks, and now now that we're doing 100,000, now we're calculating 100,000 means. Maybe we can use some more breaks, 1,000 breaks, and whatever. You can see that it becomes very smooth, and it looks like a normal distribution. And in fact, it is a normal distribution. So how did we get from like rolling dice to the normal distribution? The truth is that, and the central limit theorem states that if you take any distribution, so in this case we took dice rolls as a distribution, which happens to be a kind of uniform distribution. If you take any distribution and you collect sample means from that distribution, so we did that by rolling 100 dice, taking the mean of the values that come up on the dice. So the mean of if you roll, you guys understand, taking the values that actually come up on the dice, taking the mean of that. We took 100,000 of those means, and the more of those means that you take, the more that the distribution of the means looks like a normal distribution. And that's true of any distribution. So that's true of flipping coins. That's true of the distribution of like, if you were to stand, on the first day of the spring semester, if you were to stand in front of the door of Schaefer Hall and measure the amount of time in between people walking through the door, once you get enough people, that the means of taking those samples of people, of the amount of time in between people walking through the door, that will converge to a normal distribution. And so this is a very powerful idea and is one of the central ideas of statistics. And so I couldn't resist illustrating it for you in R, because it only took us a couple lines of code and like 40 minutes to show this. And if you're not convinced, it's a great opportunity to fool around with the other distribution functions in R that look nothing like the normal distribution. And if you take enough sample means, it will converge to looking just like this histogram. So, it's kind of an aside, but I don't know. I thought it was important to mention. All right, so that is what I wanted to say about statistical functions in simulation. Does anyone have any questions in general? Okay. All right, so in that case, let's talk about modeling. Modeling in its broadest terms is you acquire some data and you try to make predictions about the future using data that you collected. So for this exploration of modeling, we're going to there are some data sets that are built into R. This one is called trees, and it is measurements of 31 trees, and it's their girth, their height, and their volume. If you want to know about the units, or if you want like a reference of how this data was collected, you can look at the help page. But it doesn't, that stuff doesn't like apply to our discussion right now. All you need to know is that it's 31 trees, 3 different measurements, and we can illustrate some nice things about linear modeling with this data set. So linear modeling is, the word linear and linearity has to do with drawing straight lines and basically drawing the best straight line that you can draw. So if we plot, let's see what I wanted to plot first. So if you plot the girth of these trees, which is their diameter, and the volume of the trees, what you get is this relationship that you could accurately describe as like a linear-looking relationship. In other words, you could imagine drawing a straight line through all of these points, or you could imagine drawing a straight line, and that line would hit many of the points, and the points that you didn't hit would at least be close to the line. And so building, there are other kinds of models. Not every relationship between data points is linear. And there's all kinds of modeling functions and libraries that you can download for R and that are included in R. But linear relationships are kind of the most easy to understand because they're easy to graph and they're easier to think about. So that's what we're going to talk about. So to construct a linear model in R, it's pretty easy. You use this function called LM, which stands for linear model. And linear model can take several arguments, but most of the time you're safe with the defaults. 2 things that you need to specify is a formula, which is kind of, it's like an advanced data structure in R. It's not something that we've dealt with yet, and not something you deal with all the time, and some actual data. So to construct a formula, you take a look at the data set that you're using. In this case, we're using this trees data set, and let's say that we want to predict the volume of a tree based on the girth of that tree. So in order to create a formula, we're going to say volume, and then the tilde, and then girth, and that's our first argument. This tilde takes these 2 variable names, even though we haven't defined them, and it creates this formula data structure. Of course, volume and girth don't have any meaning outside of this function that we're constructing, and in order to give them some kind of meaning, we have to specify the data argument, which is this trees data. So when using a linear model, you have to make sure that you have, trees as a data frame. The column names of trees, are girth, height, and volume. And so you have to make sure that the column names in the data frame that you're using are set up and that they correspond to what you're specifying in this formula. Any questions so far? So if we run this code, we get something interesting printed out. The meaning you can take away from this is that the y-intercept, the y-axis being volume, just like the way that we plotted it, for this linear model that we've built, which is literally a line through these points, the y-intercept is negative 36, whatever, and the slope is around 5. So we can plot this line easily, and what I'm going to do is I'm going to store this model inside of a variable called tree model. And once I execute this line of code, you can see the tree model, this tree model variable kind of acts like a list insofar as that you can use the $ operator and you can extract different values from this model. We're going to get into a few of these values later. But right now, we've got this model stored inside of this variable. We've plotted trees versus girth. And now we're going to plot the line so we can kind of visualize this relationship. We can do that using abline, which we talked about on Monday. And with abline, normally you'd have to specify the y-intercept and the slope, but we can actually just give it this tree model. We can just give it the model as an argument. And when we execute that code, it'll draw us the line. And so this line is a line such that each of the points on this graph are a minimal distance from this line. So this line has been fitted and has been optimized so that sort of like the absolute value of the distance, the sum of the absolute values of the distances of all the points between the line and the points on this graph is minimal. Do you guys understand what I'm saying? That was a chunky phrase. So we've got this linear model. We've plotted it. Now that we have this model, we can make some predictions about tree volume if we get data about tree girth. So I'm going to create a data frame called fake trees. And this data frame is only going to have one column, and that column is the girth. So I'm going to make up some girths. We'll say 12, 14, and 16. So I have this linear model stored inside of tree model, and I can use this function called predict. And all I have to do is pass 2 arguments to predict. I'm going to pass it my model, and then also this data frame of fake trees, which only has a girth column. And what I get back is predictions of tree volume based on this linear model. And so as you can see, if I plot these points on top of this graph using the points function, let me save this as a variable and call it, here, you know what, I should do this more often. Predictions 1. So I'm going to store these predicted values inside of this variable called predictions 1. Then I'm going to plot these predictions. So my x values, my girth values are 12, 14, and 16. These predictions are my y values, or the volume that I've predicted. I'm going to color these red so that we can see the predictions in contrast against the data that we have, which are in black. Okay, so as you can see, these points are exactly on the line. So we've built this simple linear model, and we can give it x values, we can give it values for girth, and we can use the predict function with this model to just generate values that lie exactly on this line. So, that's pretty good. At least we know that, at least we can say that these predictions are in the realm of the data that we've collected and are based on that data. But if you noticed, looking at the tree's data frame, there's some data that we're not using, which is this height data. So if we look at, we're trying to predict a volume, and so if we look at the height data and the volume data in a plot, you can see that there's, a general, you could say it's a linear relationship that, you could imagine drawing a line through this, but it's not as, the relationship isn't as defined to the naked eye as the relationship between tree volume and girth, as you can see. So, but all because, or really I should say just because the relationship is not as clear, doesn't mean that these data aren't valuable in creating a more accurate model for predicting tree volume. So to create a more complicated linear model, you can add variables to this formula that we specified within the model. So to add a variable, I'm just going to say plus height, since now we're using the height. I'm going to call this tree model 2. So we still have the old tree model. So now I'm creating a linear model, a multivariable linear model that takes into consideration both the girth and the height. And the problem with teaching this that we're going to run into is that now we've left just being in 2 dimensions of volume and girth. So I am not going to have a line to plot for you to kind of demonstrate this linear model, although I'll be able to plot the predicted points. So I just create, does anyone have any questions? That was a lot. Okay. So I'm going to create this model and execute this line of code. And it gives us a new model, tree model 2. And we've got our fake tree data frame still. I'm going to make a new set of predictions that I'll call predictions 2 with tree model 2. So we're using the same fake trees. I'll make some new predictions. And subset, probably spelled something wrong. I'm sorry. Okay, so we're all right. So before, when we were trying to make these predictions about fake trees, we specified girth. Now that we've built a new model that takes 2 variables, we have to provide 2 variables, which I forgot to do. Before I came up with some variables that worked nicely, here they are. So I'm just going to create these. I'm just going to specify that in our fake trees now we're specifying girth, and we're going to specify. Let's see. We're going to specify height, and these are just some fake heights that I came up with. So we have a fake tree that has a girth of 12, a height of 70, and then another tree that has a girth of 14 and a height of 73, etc. So I'm going to create this fake tree's data frame, and now that we've defined height, we can make a prediction using this fake trees data and our second tree model that incorporates height. All right, so that is much happier with me. If we compare these two predictions, we can see they're a little different. And then what I'm going to do is I'm going to plot girth by volume, and I'm going to plot our old line. So the line that's plotted here is the first linear model that only incorporates girth and volume. And then I'm going to plot our predicted values from the second linear model that also incorporates height.
Why did you not label outline tree model 2?
Because I can't plot this linear model in one dimension. If I were to try to do this, it'll give me an error. And see, it creates it just draws a line that incorporates the height, and just by coincidence, that's like off to the side of this graph. If this line could be totally off of this graph, and then we wouldn't even see it. We would get a warning, and it would see that function's doing nothing. So the reason I want to show this line, though, is because I'm going to show you that the predictions from our new model don't fall exactly on this line from the old model. So we're using the same girths, even though I'm about to plot the predictions that also incorporate volume. And then I'll plot those predictions. Oh, actually, let me plot them in red so you can see them. Whoops. All right, so as you can see, they're near the line, but they've been reduced a little bit. That's the effect that incorporating the height data into the model had. And also, as you can see, the distance, the purely vertical distance from the point to the line is different for all three predicted values. This one's a little closer, this one's a little farther, and this one is farther still. It is not totally clear. In fact, I can, if I replot this and I trim it down a little bit, it'll be easier to see. So if I say that the x limits are between 11 and a half and 16 and a half. Yeah, maybe now, or if I make it smaller, you can see how these predictions are as these predictions get higher, they are drifting towards this line. And if we make more predictions, they'll probably, all the way into some large girths, so they'll probably cross this line. Does anyone have any questions about that? Or about modeling in general? I really only have one other thing to show for modeling. All right, so the only other thing I wanted to show is that the same thing is going on when you plot girth and excuse me, when you plot height and volume, and then you plot these predicted values for volume, but except this time we're using the girth, these fake girths that we came up with. You can see that the predicted values are in the realm of what we might consider reasonable within this, within the data that we've collected. Of course, if there were more variables, you can imagine the kind of variables that you could have for trees. I don't know, like number of branches, or you could even have a variable that has to do with like location or like average temperature. I'm not an arborist, so I don't really know, but you could keep adding. Where's my model? Oh, here. You could keep adding those variables into this model as long as you had data for them. And hypothetically, you would get a more accurate model. Of course, the more data you had, so if you had more than 31 trees, you would get a model that theoretically would be better at predicting at predicting the volume of other trees. And so, yeah, that's some of my best advice to you, if you're interested in doing data analysis, is to have as much, to get your hands on as much data as you can. With more trees, we could probably build a better model. Does anyone have any questions about this? This is like the tip of a very complex but also a very interesting modeling iceberg of all the different kinds of modeling you can do in R. But I hope you guys, think that this is interesting. You can, I just showed you how to make predictions about the future. I think that's a pretty powerful thing. Okay, so are there any questions? Sorry. Okay, so for the last 25 minutes of class, I want to talk about something we probably should have talked about before, but I could have organized it better, but I don't think there's been any harm, which is just getting data in and out of R. It was kind of difficult to motivate this before because we didn't have any data to get out of R. But now that you guys know all of this stuff about simulations, if you want to send 10,000 dice rolls to a friend, you might want to know how to do it. So there's all kinds of different data. I mean, there's an unbelievable amount of data that you can get from the internet. There's data that you can get from what are these things called APIs, which are just like computers that have data on them and make it available to you over the internet. There's all kinds of medical and genetic data that it has sort of like complicated formats and so forth. So I'm going to go through probably the kinds of data in R that you're most likely to see generally. So one note before we get into it is that we use this trees data set for this linear modeling exercise, and R comes with a lot of data. And I was discussing this with a colleague, and whenever someone writes a new R package or a new function and they want to show it to you, they always use this data that's built into R. And so to me, it's kind of stale, but I've been using R for years. You guys presumably have just started using it, so if you want to practice your skills and you don't want to worry about getting data into R, there are a lot of data sets that you have on hand that you can just start exploring and using, and I really recommend that. You can look at all these data sets by using the help function, and actually it's something stranger. If you use the help function and go to data sets, it'll tell you how to do it. Yeah, so for a list of all the data sets, you have to do library help equals data sets. Who knows why? And this window will pop up, and this will give you a list of all the data sets that come with R. And some of these are like very famous in the worlds of data analysis and statistics. Others I've like never seen used before. The ones that I would say that are particularly interesting, and I'll put a list of this on the website. This iris data set gets used all of the time. These are just measurements about irises, which are the flower. Also, there's the trees data set that I used. There's this data set called empty cars, which is just a small data frame of some information about cars relating to like the horsepower and the miles per gallon, and you can, it's a small and understandable data set that can be cool to do visualizations with and build models with. Like this air quality one people use a lot, and this Titanic one is very famous of who lived and who died on the Titanic, and there are a lot of interesting visualizations you can do to kind of see how, if you were a rich woman in first class, then you were like guaranteed to live, where, if you were a poor man in steerage, they like all died. And so when you're trying to visualize like how groups kind of move from state to state, or how really what I mean is like how different attributes of like an individual, how that affects their outcome. The Titanic data set is used all the time. I have like bookmarks of how these different data sets are used, and I'll post some of those to the website. I encourage you guys to explore these. So now back to getting data in and out of R. So when we were looking at that Lego data set, we used read.csv. You can, if there's just a file on the internet of CSV data, you can provide that URL to read.csv. Also, do you guys know what a CSV is? I talked about it a little bit in one class, but I'll be more explicit now. CSV just stands for comma-separated values. And what it really is, in its simplest terms, you can think of it like a spreadsheet. If you've dealt with Excel and spreadsheets before, there's no like logic, there are no formulas embedded in CSVs, but you can embed values. So if I create in Excel a very simple spreadsheet, whatever, just matching the keyword with some values, I can save this data. And what happens is that like data sources, especially online, distribute data in spreadsheets all the time. So to get it into R, a simple thing you can do is you can save an Excel spreadsheet. Instead of saving it as XLSX, you can save it as comma-separated values. And we'll just call this workbook 1. It will give you this warning because by saving as a CSV, you're throwing out any formulas that might be in this Excel spreadsheet. If you don't know much about Excel, then like don't worry about this. But don't worry about what I'm saying. So you can just click continue. It will just save these flat values. So I'm going to quit Excel because every moment I spend in Excel kills me a little bit. And so here's our workbook 1.csv. And so to get it into R, we can do read.csv, and all we have to do is specify the path. So we can just start out with a string, and in RStudio, I'm still in the working directory of lecture 3. When I was showing you guys about how files and working directories work. So I know it's on my desktop, so I'm going to go one working directory above using the dot, using that notation. And then there it is, my workbook 1.csv. So I've got, this is a relative path to the CSV. There are some other arguments that I need to specify. So the one argument is header. Like we saw in the trees dataset, this dataset has these headers, these column names of girth, height, and volume. In this workbook, I didn't include, come on, Mac, it's a tiny file. All right, I'll open this back up in Excel. I didn't include any column names in this, example toy CSV. So in this case, I would say header is equal to false. If for some reason, there were column names like number of trinkets, and then this is like widgets. If for some reason I had column names like that, I could specify header is equal to true, and then that would prevent these column names from ending up in the first row of my data frame. So as an example, let me just show this to you. So if I delete this row, I'm going to save this CSV. If I say header is equal to false, it will automatically make these column names of V1 and V2, and it will import this data as a data frame. If I said header was equal to true, it will think that 1 and 46, the first row of this data set, are in fact header names. As you can see, and because they're numbers, a column name cannot start with a number in R, so it just automatically adds a capital X. So if I did provide column names, if the column name of this was just X and the column name of this was Y, and I saved this, and I did read.csv header is equal to true, it will just provide the column names X and Y. Well, it won't provide them, it will read them in from this CSV. If I said header is equal to false, it will think that X and Y are the first row of this CSV. As you can see, then it just assigns V1 and V2 as the column names. Another read.csv takes a lot of arguments, but another important argument to specify is this argument in strings as factors. In a previous class, I think it was lecture 2 or 3, I think it was 2. We talked about factors and how they're this data type like a string or a numeric or a logical value, but they're not used as much anymore. By default, anything that R infers as being a string, for example, X and both X and Y are a string in this case, it will turn it into a factor. And you usually don't want that. And so whenever you do read.csv or, spoiler alert, there's a write.csv, which we'll talk about in a minute, you want to specify strings as factors equal to false, which it stinks that the default isn't false, but the default is true. And so in order to prevent yourself from getting burned, and you know that the data type you're getting in is a string, you've got to say strings as factors are equal to false. I would say that these two arguments, header and strings as factors, are like the most common concerns when reading in CSV data. So write.csv is extraordinarily similar. For the first argument, we specify a data frame. A data frame that I have on hand is this trees data frame. So I'm going to type in trees. Then I have to provide this argument file, which is just a path. So my working directory is still this lecture 3 directory inside of my desktop folder. So I'm going to just specify the directory above me by saying ... and I'm going to call this trees.csv. And then the other arguments that get specified most commonly are row names and column names, but the defaults for these are usually what you want. So if you write, if you specify row names to be equal to true, it will add a column to your CSV that is just the integers that correspond to your rows, as long as those are your row names. So as you can see, in this trees data frame, the column names are girth, height, and volume, and the row names are 1, 2, 3, 4, etc. Most of the time, you don't want to write the row names because they're just kind of redundant, and when you import the CSV again using read.csv, you'll get the row names back. There are situations where you name the rows. I don't personally recommend naming rows in data frames, because if your rows are important enough to name, then you probably want a new column, because you're actually specifying some variable. So I recommend setting row names equal to false. And the default for column names is that it's equal to true, and you usually want the column names because the column names provide a minimal description of what the data is that you're writing. So I'm going to say write.csv trees, that's the file that I want, row names equal to false, I execute this line of code, I don't get anything back. Here is the file, and if we open it up in Microsoft Excel, we've got our trees data frame now as an Excel spreadsheet. So read.csv and write.csv are wonderfully useful. The other, another read and write function that I want to go through is these RDS functions. There we go. So there are these two functions, read RDS and write RDS, and they are ways of saving your variables as these files that are specific to R. So doing this is only useful if you're going to be giving your data to someone who's going to open your data up in R using read RDS. But the reason that you'd want to use RDS is because RDS files are they're like maximally compressed. So if you're working with a large data set, if you simulate 100,000 dice rolls or whatever you're simulating, and you know you're going to be giving that to a person who's going to be reading it in with read RDS, the saving it as a CSV potentially could be a much larger file than saving it as an RDS file. And save RDS and read RDS work. The arguments are nearly identical to read CSV and write CSV. I wish it was read and write RDS, but we can't have everything we want. So with save RDS, I'm going to save trees, which is this data frame, although you can save anything that you have stored in a variable. So you could save a vector, you could save a list, or a data frame, or a single value, anything you have stored in any variable you can save as an RDS. Then I just, not spelling today. Then I just can specify a path. And again, I'm going to write to the desktop, and I'm just going to say trees .rds. These default values are what you want to do 99% of the time. So if I execute this line of code, here I now have this RDS file, and my computer even knows that this is a file that's associated with R. If I then go to read RDS, and I specify the path, it will load this RDS file directly into memory. And if I want to store it in memory, I need to assign it to a variable. So I'm just going to call this trees2. And whatever data read RDS reads into R stores it in trees2, which, as you can see, is identical to trees, which I saved. Any questions about RDS or CSV? All right. So the last reading and writing data that I'm going to squeeze in here in the last 6 minutes is read lines and write lines. Of course, I also wish that these, read has it's like read.csv, save RDS, and read RDS don't have dots. Then there's the syntax for read lines and write lines. So write lines is very universal in that you just write, you give it a vector of strings, and it writes that vector of strings to a plain text file, to like a .txt file. So, I can, one of the default data sets in R is letters, which is just a vector of all the letters in the alphabet. And of course, if you do capital letters, it's a vector called capitalized letters. So if I just give it this vector, letters, I then give it a path, and I'm going to call this letters.txt, but I'm going to put it in the desktop, so I'm going to store it one path above my working directory. And then I can specify this argument called sep. The default value for sep is this. We will get into this in a later lecture. The default value for sep is this string, which this \n represents a new line. So what that means is that the separation between each of these strings is going to be a new line. So once I open this as a text file, it will just be A, and then on a new line B, and then on a new line C. If I made this sep like a space, it would all be on one line, and it would be A space, B space, C space, etc. But I'm going to leave this as a default so that every single string that I'm writing is on its own line. And then this use bytes you usually don't have to worry about. So I'm going to say letters, and we're writing it to this letters.txt. Here's the txt file. And as you can see, it's just a plain text file with all of the letters written on separate lines. At the same, in the same way, you can do read lines. You provide it with a path. I'm going to provide it with the path to this letters text document. That should work alone, but let me see if there are any other vectors or any other arguments I want to talk about. If for some reason you only want to read a certain number of lines, you can specify that in the n argument. But if you leave it by default, it will read all the lines of whatever you're reading in. The rest of these arguments you usually don't have to worry about. So if I do read lines, I just give it this path to this text file. It'll read it in as a vector. And I can store that vector in a variable if I so wish. And as you can see, if I go over to letters.txt, I open it up in a text editor. The default, I like this program called Sublime Text 2, but the default text editor on Mac is called TextEdit, and the default text editor on Windows is called, there's Notepad and WordPad, they're equivalent. So if I change, line 18 to be and then I read that in after saving it, then it gives me the string R is great within this vector where each line is its own string. Does anyone have any questions about this? Okay. Well, that's the end of today's lecture. The next lecture is in a week, on Wednesday next week. And then the last lecture is on Friday next week. If you have any questions, let me know. I will be posting some swirl exercises for you to do that will have to do with simulations and the statistical functions that we talked about. And I'll figure out what was tripping me up before when I was trying to plot that normal distribution. But thank you all.